Joshua, why don't you draw this one? She was drawing that. Okay, spherical.
So this is the magma chamber.
Yeah.
It's- okay.
And in this case, yeah, that 400 degrees, we can say that it's far, far away is where it's fixed at 400 degrees. So we can kind of let the energy go wherever it wants, the heat go wherever it wants. And that one starts out at 1,000 through the whole of the inner circle. What will that one look like as it cools? What are some things we need to think about with that? So maybe do a profile through the middle of it. And we can say it's 400 degrees, 400 degrees, and then 1,000 degrees in like a square wave.
Huh. That's super
So
weird.
it ignored everything you wrote before
Okay.
that and just did the line.
So
Weird.
1,000 degrees on the top of screen.
Well, yeah, so this whole area, so if it's 400, 400, 400, and then 1,000, and then back to 400.
So this is okay. 400. So 1,000 is
Can you just draw the profile? Like
like
a square wave, basically? Well, this is a hard, so this is a very, we're drawing, the temperature along this line, what happens right there? Initially.
Did you say 1,000?
Yeah.
degrees?
So it's gonna jump straight up to 1,000 degrees right there, because we just emplaced this magma.
Okay.
So let's draw a plot, and you can draw it down here if you want, but it'll jump up to 1,000 and then back down. So.
Okay.
And so how does this one change through time then? And what are some key things? What is the spherical, how is the spherical symmetric going to make it different than the pizza?
It'll radiate energy faster. Or diffuse energy.
Yeah, the surface area to volume is different, and it's also emitting out in all directions. So in this case we don't have goo surrounding it, we have rock surrounding it. Will that heat up slower or faster?
Depends on what it is.
Depends on what it is, yes. But as you radiate energy out, what happens to it if it's in a sphere versus in a straight line?
Oh, it spreads out further.
Yeah.
Like,
The energy spreads out,
I don't
so
know how to.
it takes longer.
It's not.
Yeah, so there is going to be a subtle
Surface
difference in
area.
this. Because as you try to heat up this next layer of rock, the energy that's coming from here is getting spread out as it tries to heat that
Like
up.
a lot more
So
places
if-
to go.
If it were a linear problem, all of this energy would go straight into this chunk of rock. But in this case, we're spreading it out, so it actually won't heat up as quickly as you go farther out, because your rings, the volume that you're trying to heat up will get bigger and bigger. So what does it look like at the next step here?
So like a little bit this.
And what's going on inside?
It's be lower. This.
Right, so the middle will stay hotter longer, will cool a little bit on the edges, warm up a little bit on the outside.
Mhm.
The center will stay molten, will start progressively, probably progressively recrystallizing this depending on the, depending on what the mineralogy is. What happens next?
It will get steeper and steeper.
Yeah, eventually this will come down, but it's probably not gonna all come down together. So it's probably not gonna do this, it's probably gonna continue to go in this way a bit more. But how fast are we transmitting heat when this is our temperature gradient compared to this one?
It gets slower as you get
Slower.
cooler.
Right, so this is a very strong dT/dx.
Mhm.
So it's gonna transmit heat as fast as it can. Initially when this happens, we'll rapidly go from there to there. But then here, our dT/dd is smaller, so our heat flux will go down.
Mhm.
And so it's gonna take longer for it to go to there, and then longer and longer and longer. So that dependence on the slope is gonna make it take a much longer for every same step in total amount of energy transfer. It just takes longer and longer to do that. So that's where, you should, if you kind of know intuitively what to expect in these problems, then it's much easier to catch your mistakes or know where you might be headed in terms of modeling. Okay, one more quick version of this, I think. No, maybe not. The one thing we haven't done a lot of in these discussions is include advection in the system. And all of our steady state solutions, they've all been linear so far, right? It's always like, well, what's going on in the wall? Steady state, it's going to be linear. It might be curved getting there, but we almost always approach a steady state or a linear solution. But when you add, you can still have a steady state solution for an advection system if your velocities are constant. What are some examples of an advection and diffusion question?
The geotherm of Io.
The geotherm of Io. Explain that.
The crust is being advected down at a relatively constant rate of about 1 centimeter per year, and there's a magma ocean underneath it that keeps it, that convects pretty well and stays at about a constant temperature.
So we have, is there new crust being formed
Yes.
then? Cool, we're gonna simplify this to the 1K version. So we have a new crust layer being added on top, and it's moving down at 1 centimeter per year. But then deep down here is our mantle, which can conduct away the energy as needed. So we want to make that then a constant temperature boundary, assuming that the mantle can handle all of that and keep it at a constant temperature. Our T surface, super cold presumably.
About 90 Kelvin.
So without the advection, the solution solution is gonna be the linear if it's in steady state. But in this case, we're adding a little bit of mass that's at that 90 Kelvin and moving it downwards at a centimeter per year. So how is that gonna change our steady state solution? You probably know the answer to this, so we'll let somebody else answer.
So we're constantly adding a colder material to the
Constantly adding a
system.
colder material. So let's just look a little bit below
Yeah,
this
it's
one. How is constantly adding gonna change the temperature at just a little bit below?
You're also shoving the crust down. If that helps.
So everything, is it melting the crust at the bottom at the
Yeah.
same? Okay, so we're melting the crust at the bottom. We're taking away the same amount of crust at the bottom.
Temperature's gonna be lower at the top.
So it'll be a little bit lower than what our steady state predicts. And what about down here? So this is our minus 90. If it's going really fast, that one will get down there and it'll almost be the same as the 90
Yeah.
Kelvin. But yeah, it'll be lower.
yeah. So the colder stuff drops down, and then it's colder, but then that creates a greater gradient, and so at some point the slope increases. So it starts out with less of a slope, and then the slope increases at some point.
Yeah, so we should end up with something probably looks like that. What if we increase the speed?
Lower still.
Yeah, it's gonna push this down faster.
So I know that it's the tidal pulling heats it up. Is there any of that tidal pulling that's acting as like a heating force in the crust area as well?
No.
Okay.
So a steady state advection problem is going to be our curved solution, and the curvature will depend on the speed and this thickness and the thermal properties of the conductivity. So this is where we have, just like the Reynolds number in the fluids model, this is what's called the Peckley non-dimensional number, where we have the relationship between the advection and the diffusion term. And so in wanting to solve this problem and figuring out what we're gonna get rid of out of our equation, we can do the same thing we do with the Reynolds number, and that's say, well, if this were a millimeter a year instead of a centimeter a year, maybe it's such a minor adjustment to the profile that we can just ignore the advection. Or if the diffusivity of the material is such that diffusion will happen so fast, it's highly conductive material, maybe then even the centimeter a year is fine, but it still is gonna have a minor effect on the solution. So by coming up with the speed that you're advecting things at relative to the properties of the material, you can look at whether or not advection is gonna dominate your system. If this were going really fast, then advection could totally dominate the system, and the diffusion might be a totally minor part of it. Or vice versa, your diffusion might dominate, or you might need to have both in which case you would keep both in and you'd figure out, based on the Peckley number, about what curvature your system might have in here. And these do the simple versions of that with advection and diffusion. There are some analytical solutions for. So once you get it down to simplify it down to as simple as you can get it. Is it one-dimensional or is it spherically symmetric? How many dimensions and what terms do we have and what magnitudes we have? There are a lot of solutions already out there for an analytical version of the advection diffusion. And if it gets too much, or if you want to be able to put, for example, if the convection within the mantle creates fluctuations in the temperature of the base, then maybe you want to model something with that, and then you would need to go to the numerical solution. So, but none of these problems, they might require numerical solutions, but I know I've said this a million times, like what I hope you come out of this class with is an understanding of how to think through the setup, the boundary conditions, and kind of how to simplify them down to something that will allow you to answer the question with the simplest model possible. Because there's no need to go to a crazy three-dimensional giant model if you can make enough assumptions to put together a relatively simple model. And like I said before, you can still publish papers with simple one-dimensional analytical solution models that are quality research papers. And sometimes they're the best papers because people have really thought carefully about the system and they haven't. Sometimes people use fancy 3D models as a crutch because they exist and they look cool, but you almost can do better science if you force yourself to really think about what are the essential processes going on here, and can we solve this either purely analytically or with a relatively simple model. And then at some point you might need to go to a more complex model, but it's always better to start with a simple model. So yeah, on Thursday you guys can do a few in-class projects just to kind of see how this really ends up working in a real-world environment, and try out a few different things, and hopefully this little FLIR will, and the other temperature sensor will have good enough resolution to give you guys a sense of what's happening, because you can watch it change through time. I'll give you a little electric kettle so you can heat up water to make things thermally different.
You said you'll sort of give us some written instructions on how to do these then?
Yeah.
Okay.
Yeah. And then you can just grab books off the shelves here and to create your slab system.
The layers.
Mm-hmm.
Said the different layers.
Mm-hmm. Which means you need to think about which books here have different conductivity, material properties, and if you want them all to be the same, or if you want to have different ones in there.
Yeah, all the same. Just grab those.
Okay.
Keep it uniform.
Quick break. Someone need to move into microstructural rheology for the last stretch.
I went to a Women in Physics conference at Georgia Tech in my undergrad, and went to a talk that was dealing with rheology, and they were doing the guy talked about how he was working with ants and how they could be solids.
The ant?
Yeah, so it was neat that I went up to him afterwards and like, do you guys have any way to make models that would apply to like the Earth, the rheology like mantle moving and stuff. He's like, we don't think about rocks as much. I'm like, okay. He's like, I think that's a different sort of scale. I'm like, oh, okay, well, ants are cool too.
Ants are cool too, yes. Okay, so dig deep in your mind and bring back our springs and dampers. That was our one-dimensional version of thinking about rheology in its simplest form. Well, simple in a certain way. Just kind of just to kind of tie, I can't draw on this. So this is just a combination of the Maxwell and the Voigt model, but it's one that kind of combines a bunch of the processes that are going on in the Earth's mantle. So if we put a stress, if we apply a stress at a certain time and then turn it off at another time, we have the spring is an instantaneous elastic response, right? So this is our strain through time. Strain, not strain rate. So we know that the spring is going to give us an instant elastic response. So we're going to have some amount of strain that comes immediately at the time that this stress turns on. What is this one going to look like?
It'll just increase linearly.
Right, so it's a linearly increasing strain because it's a constant strain rate. So we know we're also going to have some of our strain is going to be a perfectly linearly increasing strain. And then what is this double?
Does it make a curve?
Yeah, and what's it is going to make a curve
Upwards.
that combines
Oh.
these. But why does it make a curve? Kind of a term for it. It's not fully elastic. There's a
Viscoelastic.
spring in there.
Viscoelastic.
Well, it's all
Yeah.
viscoelastic, but yeah, so it's not an instantaneous elastic response. What does the damper do in there? The spring wants to respond instantaneously, right? But what does the damper do? You got it, Josh.
It's holding it back, like don't go too fast. Like
Exactly.
I'm slowing it down.
Exactly. It slows it down, so it's a delayed elasticity. Delayed elasticity. And the reason and you could put a lot of different values in here for to make the different effects, but generally what this ends up looking like, because this one is the instantaneous elastic up to a certain point. This one is always it will reach its final elastic state. It just will take a little bit of time. That delayed elasticity, it might be curved like this, or it might be curved way out like that, but its curvature might vary, but it's always going to reach that eventual amount of strain due to that. So here we have E of the spring, and then here is the E of the that Voigt model, and then And then after this is done, this is going on a bit as well at the same time, but ultimately it will take over because it never ends. As long as the stress is on there, this guy is going to keep going as long as you apply a stress. So eventually the whole system is gonna settle down after the time frame has passed for the instantaneous and then the delayed elasticity. This guy is gonna take over and just gonna keep going forever and ever until we take that stress off. So the final strain will depend on how long we leave it on. If we leave it on longer, then this guy will keep going up. Somehow it's working better now that I've got it right next to it. But when we take that off, how much of this strain do we get back? What do we get back?
What do you mean? I'm not sure I understand.
Well, with a spring, we stretch it, we let go, and it goes back. With a viscous material,
it takes longer to get back. You don't get all of it back though, do you?
do you get any of it back? It's purely viscous?
Purely viscous, no.
Okay, so we're not going to get any of this back.
Just like an old elastic.
We will get this back. And how much of this do we get back?
That curve, little curve, we subtract. Yeah.
So
The
we
middle.
we will eventually get it all back. It just will take time again. So
That's the part I thought you were talking about.
So if this is the end of our, so in the end, did I get that right? No, I didn't, sorry. It's not that line. This too, we'll get E1 back and ES back. It's this that we don't get back. And so if this is only that much, this might come down to there. Where this is, what I said, I don't know why I said EV. We're gonna do EV. VS plus E epsilon S. So this is this. We get that back. But our fixed bit is this part here. We don't get that back. So our net strain will just be this top part in the end if we take it off. So is that coming back to you guys, some of these details? Okay, so in the Earth, these represent different timescales of processes going on. So this general model actually can do a pretty good job at capturing a lot of what goes on in the Earth. What are the instantaneous or really fast elastic processes that happen in rocks in the Earth?
It breaks off the slab. When the slab breaks off in the subduction zone, it creates a big earthquake. Because of that.
So an earthquake,
Yeah, like,
I would say, when the slab actually breaks off, that might be kind of smaller, a slower process.
and that's not necessarily elastic, is it? Slab breaks
Right,
off.
it's breaking off. So what about the earthquake though? Because that's where you were going. What is it in the earthquake that's fast?
So I know, like with a transform vault, it sticks and then it goes.
What does an earthquake create?
Seismic waves.
Seismic waves. Super fast seismic waves. Scale of a second, smaller. And you can have the whole Earth oscillating, right? From the big earthquakes, you get the bell sound, that's all still pretty fast seismic. What are some medium length scales? So like what kind of changes happen on like a yearly or daily to yearly scale that change on the whole, kind of on the big scale of the Earth?
Maybe like tidal changes?
Yeah, tidal changes might cause some wobbling. Those are probably, I mean, if you were wanting to model the whole mantle, you might need to incorporate that. It might be a pretty small magnitude, but it's the right time scale, yeah.
Seasonally, some areas accumulate a lot of snow, and so that adds a whole bunch of mass to it.
Right, so
over a
you're
large
changing
area.
the moment of inertia of the whole Earth, and so if
Yeah, well, I mean, that sort of like the kind of the idea of isostatic rebound and stuff like that. Like, put a bunch of mass somewhere for on Alaska for a few months. That probably has a
you
little bit of
deflects, yeah, it does, it causes
push
an
down.
elastic deformation of the crust, yeah. Yeah, and that's definitely true, and Jeff's gonna start with you guys on that on Tuesday. And then let's get, so those are all within the, within the kind of instantaneous to maybe just a little bit of the delayed elasticity kind of system. What about our longer time scales? That's where you get into the
Slap.
slabs descending.
Yeah.
Mantle convection, the whole, and the longer term post-glacial rebound, when you actually have the mantle flow coming in. And so this version of thinking about strain in the Earth on the short time scales, change color. You know, we are down here bouncing up and down, and then some things we might get up where we go through a little bit of the delayed elasticity on some time scales. And then eventually with some of these longer term processes, we start to get into the viscous deformation. So this, combining all of these, we actually can do a lot in terms of Earth models when we combine all of them together. And you can look at this, just since you guys have seen a lot of stresses and strains lately, you can write this all. Write this all out in a way that you could integrate into the equations that you've been thinking about. So this is our elastic, delayed, elastic, with that time constant in there. It's a transient response. And this is your long-term viscous. But what is it, in terms of the rock itself, which is a polycrystalline material, how is it able to express all of these? Who here has had enough rheology to have some ideas on what's going on the, we actually talked about this in one of those first days. What's going on the micro scale that allows for an elastic response in a crystalline material?
Or the bonds.
Hmm?
Bondings between the
Right, so the bonds start stretching between,
it doesn't turn back completely.
these are molecules, we have bonds between them.
defects in the crystal lattice.
Right, so the initial elastic is just bonds stretching but not breaking. And that's why you can recover all of that. They literally are, the bonds are acting like the springs. But the the viscous and the delayed elasticity under certain conditions both result in breaking of bonds, which is where you get these defects in the crystal lattice. Escape out of this. Yeah. If you did have a perfect crystal without any defects in it, if it really were a perfect crystal, those elastic energy could still go through it because all those bonds are stretching. But it'd be really hard to break any of those bonds because you'd need to break them all at the exact same time, right? So if you've got a crystal that has 1 million bonds, if it's a perfect crystal, in order to do anything to deform that crystal more than just stretching the bonds, you'd have to break all of them at the same time. So a perfect crystal actually is very hard, and they don't exist in nature. But a perfect crystal is harder to deform than one with defects in it. Fortunately, they all have defects in them, and defects are pretty much how most of the deformation actually happens. There's a few different types of defects. A point defect is just where one atom is out of place for some reason, and these are just some subtle there's some subtle differences. A self-interstitial is when you've got one molecule of the same stuff, but it's just out of place. This is an impurity, so this is an atom of something different. This one is just missing. A substitution is when you have something that doesn't belong, but it's actually fits in with the lattice structure. So the bonds are there, but the bonds are kind of differently shaped because this atom is a bit different. And this one is just a funky, twisted around version where you've got things in a slightly different places. So these are all point defects. They do play a role in deforming, but not as often, only in certain conditions. And the way they play a role in deforming is that if, for example, I start pushing on this open space means that this guy only has to break a couple of bonds to jump over into that spot. So if I'm pushing here, then he's going to try to move. And so this defect actually will move this direction. The atom will go that way. And so this defect will actually be pushed towards my stress that I'm applying. These kind of the same idea. What's going to break first is always the weakest bonds. And having this impurity in there is already pre-stretching a lot of the bonds around it. So they're kind of pre-stretched and stressed out a little bit because they're having to make room for this impurity. And so if you do apply a stress, those might be the bonds that break first. But these point defects really only come into play at lower stresses. And they can also move, they have a tendency, well, all of these have a tendency to move a little bit by themselves. Because they want to, like, nature wants to be perfect. And so, if there's any way that this could reach a lower energy state by moving, it will have a tendency to figure out a way to move. But what really does most of the work are dislocations, which are not point defects in the crystal, they're line defects. And these are all these line defects. I don't remember what kind of material this is, but this says it's 5 millimeters across. And you can actually see them to a certain degree. And they do, even in a nice straight crystalline structure, they can be all twisted up and around. They're not necessarily going to stay in a nice linear structure. So they can be all twisted around. They can merge together. They can, two oppositely arranged ones can meet and annihilate each other. So if they're oppositely structured, and I'll show you the crystalline structure, but if they're in the opposite direction when they come together, they might form a perfect crystal structure and annihilate each other, so they would disappear. More often, though, they get tangled up. So what these look like, there's two main types. This is what's called an edge dislocation. And basically we have a mismatch in terms of where things got lined up in creating this crystal, so that this plane of crystals, this plane of atoms does not have anything to add on to. And again, what this does is it stresses out these bonds because they're not in their natural state there. The other type, this actually shows you smaller, and this is sideways now. But if you take this edge dislocation, so if you have this edge dislocation, it's mismatched here, it can actually move this direction. So this this atom will jump on and join this guy, and this one will jump on and join that guy, and this one will jump on and join that guy, and leave the dangling one will slowly move its way up the lattice structure. It'll do that under our stress that we apply, but it'll also do that if it senses that there's a lower energy state farther away. So if there's another edge dislocation, but on this side, say, then they can start, at a certain point, they start to sense that each other's around. There's a certain distance that they know they can feel the stress of the crystal, and they'll slowly come together and meet each other. So those kind of processes that are done without us applying any stress are called recovery processes. And they will, basically the crystal will try to slowly heal itself if it can. But we also, if we apply stress, we create these defects as well. Whenever you push on a crystal, you actually generate new dislocations or new point defects, depending. So this is one type of this line defect, and it's called a line defect because it affects an entire line of crystals, an entire line of atoms. Sorry, I keep saying that. The other one is called a screw dislocation. And if you can see here, what's happening is that it got messed up back here, and now there's an offset between what was connected together nicely down here and what's connected together nicely up here. And so there ends up being this kind of a twisted motion, and it's a shearing in that crystal lattice. And they call it a screw dislocation because if you try to follow the line around this, you'll basically walk a spiral. If you follow the bonds around the edge of that dislocation, you'll walk in a spiral up along the whole thing, so you'll spiral. Well, in this case, you would spiral that way. But that's why they call it a screw dislocation. But it's kind of like a shear. Oh, there it is, and you can see the spirals. If you walked this way, you would come out there. You wouldn't end up where you started if you tried to walk in a circle. The movement of a screw dislocation is a bit different, and I don't like this particular diagram. This one is a little bit better. So an edge dislocation will move, if this is the edge of dislocation, it'll move perpendicular to this plane. The screw dislocation, which is this twisting motion, it's sort of like tearing a piece of paper, but it will actually, this dashed line will move itself in that way. So they move differently through the system. And you can attach them together, like if we go, there's a picture of a real crystal. Then you also have crystal boundaries. Mostly, it's kind of, there's subtle differences, but they are mostly just a pile up of a million different dislocations, such that you basically are back down to almost a liquid-like chaos. So you can create a new crystal boundary within a crystal if you take a whole bunch of these dislocations and error and point defects and line defects, and they start merging together and they get all tangled up, but all right along the same line, then they can create a new boundary. And the one way that can happen is, like, if I've got a nice crystal here and it's got a bunch of defects in it, if I apply a torque, basically like try to twist it out this way, by pushing down over here and pushing down over here, these dislocations will try to, they'll actually migrate to the middle as you're pushing that, and they'll start to get all tangled up in the middle. And so if you consistently push that, because if the crystal lattice is like this, and they'll all come together in the middle, and once you get enough of them there, actually these become basically two different crystals. And then this one might be, instead of having their crystal structure aligned, they actually will have a tilt. If you go look at this boundary, there'll be a tilt within the crystal structure.
So you say all of the defects migrate to the center, so when you have your two separate crystals after that, do they have like no defects or less defects in them?
They might have fewer defects for a little while. So there's this constant battle between the creation of defects, which happens when we push on it. If there's any localized stress on the edges will generate defects. Or if you're shearing it, so if you take this whole thing and you're putting it under stress and you're shearing it, anything that you do to it in terms of applying stress will generate new defects.
But it won't have the same defects because those migrate to the center and
exactly.
cause
So
it to break.
Right,
or
so it's
split.
a balance between how quickly are you creating defects. So if you're doing a lot, if you're messing around with this thing a lot, you might be creating a lot of defects, which could result in this process happening. But then that recovery process is also happening. Each of these defects is trying to move to its lowest energy state. So it might look for a matching defect to annihilate itself, or they will just gradually migrate to the grain boundaries, and because they can get sucked into a grain boundary, and then that would be a lower state. So you have this balance between creating defects and then recovering the defects, and depending on what you're doing, how quickly each is happening, then you will generate some amount of dislocation density, which is basically what it says, the number of dislocations per square millimeter or whatever of your object. High dislocation density means that that crystal has been under a lot of stress, it's been constantly deformed much more than it could recover, and that means it has a lot of high internal strain energy, because every one of these dislocations is tweaking that crystal lattice in a way that it takes energy to hold that bond apart, to stretch that bond. It takes energy to keep it stretched. So they have an internal strain energy that depends on the amount of depends on the number of dislocations that are in there. So the viscosity that we observe ends up being, depends a bit on the actual mineral that you're working with, but it's very closely related to that dislocation density, because if there are, you have to have enough dislocations that the dislocations can move pretty easily. So if you have too few, then it's hard to get anything to happen, because they're the ones that are actually doing the deforming. But if you have too many, then they all get tangled up on each other, and that actually can resist deformation. Have you guys heard of the term work hardening? It's used in engineering material science a lot. When you know how you can take a paper clip and you can bend it, how easy is it to bend it back?
To its original shape?
Yeah.
It's probably not going to go back to its original shape.
Exactly. The reason is that you've created lots of flaws in that crystal structure. You've created lots of dislocations. You've work hardened that material so that you can't get it back. It's got so many, it's so messed up now that it won't go back. And if you could get it back, if you heated it up, because that's what makes things dislocations move around and recover more easily. But work hardening is that process of having so many dislocations, you've maxed out on the defects in the crystal, that it's no longer that easy to deform anymore. But there's this magic mid-range where you have enough dislocations that they're easy, that they can move around. It's sort of like in a crowded room, getting something if we were in a room full of people and I wanted to give a gentle shove to one person in one corner, that shove would transmit, if there were just enough people in the room, that shove would transmit in one way if people were nicely organized and but there weren't too many of the people, you could transmit that information well. If there's too many people, you shove them and it just turns into chaos. But so maybe that wasn't the best analogy. But if there's too few people, then you're not going to be able to do anything.
It sounds like an experiment we should try.
It's like
Especially
dominoes. You want them to be close that they hit, but not too far
But not
away
too
that
far
it just falls over and doesn't affect the other person.
Right, and too close, and then it doesn't go too close, and they can't go
Yeah.
either. So the viscosity of the mantle, the viscosity of ice, the viscosity of all of these materials depends on the type of crystal, the crystal structure for that particular material, but it depends a lot on dislocation density, which is a function of how fast are you creating dislocations because you're stressing this material, how fast is it recovering? Can it recover those? And so the dislocation density is a balance between these two processes, but the dislocation density ends up helping define our material, ends up controlling the viscosity. It's related to temperature, it's related to the properties of the material in terms of the shear modulus, so how easy it is to stretch those bonds, the elasticity of the bonds. And all of those, so this is all a general concept for polycrystalline materials. There are subtle differences depending on the different materials that you're working with. So for example, so you can actually derive what you would expect as a viscosity or the shear strain rate by comparing the stress that you're applying, which is creating the dislocation density, to how quickly you're asking those, the velocity, so the strain rate will depend on how quickly you can actually move the dislocations through the material. So the speed of dislocations moving through the material will define what your strain rate is. Which is why if they get tangled up, it's a traffic jam. And if you have too many dislocations, you just can't move them, which your strain rate then goes down. So the main thing I want you guys to get out of this is that when we're dealing with earth materials, which are most of the time polycrystalline minerals or monocrystalline minerals, polycrystalline in the terms mono or polymineralic polycrystalline minerals. So they might have different types of minerals in them mixed together, or they might be like ice, which is one mineral, but lots of crystals. But the viscosity comes down to that chemical composition, the structure of the crystal, and how it responds in terms of stretching or breaking of the bonds and the moving around of these dislocations. But those underlying processes are actually pretty common among a lot of any crystalline mineral that we work with. Then you can add in little things like if you have water, a liquid phase along the grain boundary, then you might start to affect your viscosity differently as well. The reason temperature changes viscosity is because those bonds get really much easier to stretch and break and move around at high temperatures. But we also, really when it comes down to it, this is not a linear process. And so we use linearly viscous as a simplification a lot, but it often is not linearly viscous. But it still can be a really good and useful simplification. So the linear elasticity and linear viscosities are maybe, you might be able to keep those assumptions for your problem depending on what it is, but very often you see there's a squared in there, which tells you that there's probably going to be a nonlinear relationship between stress and strain rate, applied stress and then the effective strain rate when you really dig into these. This is part of where the cubic relationship for ice comes from. It's a combination of the squared and then the stress that you apply to it. So, read through the notes if you haven't already. I didn't tell you that we were doing this today. But a lot of this goes into the notes and it connects back to how we fit it into our the elasticity and the viscosity in our stress and strain rate equations. but this was just a little bit, like you could take an entire class on rheology.
Do they have a rheology class here?
No, Elizabeth
Hmm.
and I have thought about joining in forces to do a rheology seminar, but we haven't had time to put that together. Because it is a fun subject once you dig into it.